Now, let's talk about what happens when we're not under standard conditions. Sometimes we may want to know the electrical potential or the cell potential when the reactions or the reactants are not at 1 molar concentration. In fact, it's often the case that they're not at 1 molar. So, let's look back to another equation that converted from standard conditions to non-standard conditions. Right here we have an equation from thermodynamics of delta G under non-standard conditions equals delta G under standard conditions plus the gas constant times the temperature times the logarithm of the reaction quotient. Now, if you recall, the reaction quotient is just the equilibrium constant expression, except we may not be at equilibrium. So, how do we relate this to electrical potentials? Well, we're going to use our formula from delta G equals negative NFE. And so I'm going to go ahead and substitute in those real quick. So negative N times Faraday's constant times the potential, and in this case it's not the standard potential because that is not delta G under standard conditions. And then over here we do have delta G under standard conditions, so we'll have minus N F E naught and then plus RT L N Q. Now we'll clean up this equation a little bit by isolating our potentials. So we're going to divide everything in here by negative NF. So let's just do that. And when we do, we get the Nernst equation, which is the potential of the cell equals the standard potential minus, because the negative came with this, RT over number of electrons transferred times Faraday's constant, natural log of Q. Now, you may also see this written in a form that has log base 10 here, and in that, and under 25 degrees Celsius, and all of these Faraday's constant substituted in, and the gas constant put in, and 298 Kelvin put in, or at 25 degrees C, but we have to use Kelvin because of the gas constant is in Kelvin as well. So another form of the Nernst equation is this. Either one of these generates almost the same values, so you can use either of these pretty much interchangeably. Now, you might recall that I said, oh, this is the equilibrium constant expression, but we're not at equilibrium. Now let's consider just what would happen if we were at equilibrium. Well, when we're at equilibrium, delta G equals 0 because the forward reaction and the backward reaction are happening at an equal amount. So there's no net reaction forwards or backwards. If delta G equals 0, then our negative NFE, that should mean this should equal 0. Well, Faraday's constant is non-zero, and so is the number of electrons transferred. But what can be then 0 is our standard potential, or our potential. And so if we wanted to write this equation using the equilibrium constant in place of Q, we would just simply equate it to 0. So 0 equals the standard potential minus 0.0592. This can be a useful equation for determining the equilibrium constant of a reaction. If we're able to measure it using electrochemical reactions, then we can use this equation to determine the K of that reaction without actually having to measure that particular reaction. We can actually use electrochemical data or our standard potentials to determine the K if we manipulate them correctly. So that can be to our advantage and a very useful thing to do. Now, what does the Nernst equation also get used for? Because finding the equilibrium constant is important, but there are other things that we can do with it. Well, one thing that we may want to know is what would be the voltage of a cell that I create, right? Now, we went over how to determine the voltage of a cell using cathode minus anode, but that assumes that everything was under standard conditions. Because we use the standard potentials, then we could get standard conditions for our electrical potential. Well, that would mean that all of the species in that would be 1 molar or 1 bar, depending on if it's a gas. Now, if we make a battery that does not have everything in there at 1 molar, then we'll have a different potential for our battery. We can still use our standard potential, we still will need to, but we'll have to substitute in our equilibrium constant expression in for Q, put the different concentrations in there, then we can evaluate what this is and see what the electrical potential is under those non-standard conditions. And we can use that to determine the voltage of a battery that we made from that. Another thing that we could do is if we know all but one of the concentrations, we can measure the potential of the electrochemical cell, use our standard potentials and the Nernst equation to solve for the unknown concentration. Those are two very useful ways of using the Nernst equation. And I'm going to have some examples coming up.